So now we have seen a bullet proof for matrix multiplication where we have commitment for A and B, and C is public and M is public. And we have seen that this can be done with login messages. By construction, it's complete, and soundness comes from the Schwarz-Sippel lemma, and the zero knowledge comes from the use of all the zero knowledge bullet proofs inside. So, however, this is a simplified version of things that I found in the papers. So they use it, if you try to find this again, doesn't exist. So we use a simplified proof. Not sure whether the zero knowledge proof works like that as well, if you have like that. And also for the Hadamard product, this is also something which is not in the literature. I looked at the papers and I found it's really hard to understand what they do and try to simplify things. But as Einstein put it, you have to put things as simple as possible, but not simpler. And I'm not sure on which side I am here. So if you really want to use correct bullet proofs, you have to go to the original papers and implement that, because for these proofs exist. But now let's apply the things that we have done here. And this is something we do as computer science usually. We know that these operations exist. So what we do is we use a library and combine things. Yeah. Or there's a new way of programming, and the operation for this programming using libraries and doing new things, I think the operation is Python. There's a library for that. The good thing is there is a library for that. Unfortunately, it's in Rust, which is another programming language which is in fashion right now and will be the next Python. You learned Python. The next thing is Rust. So you're now rusty. Moving on. I learned a lot of programming languages in my career, and I decided to skip Python. But I'm already on Rust, so I'm a future, probably you're the past. Okay, enough programming language bashing. We don't want to have a programming language wars again like the 70s and 80s. So arithmetic circuits. So we have this operation. A is a constant. We can do this in parallel without any messages. We can do addition. We can do multiplication. And an arithmetic circuit is a directed acyclic graph. Consists of arithmetic gates with inputs and output gates. And the power of arithmetic circuits is that we can do Boolean circuits with that. We've already seen that. We can also do other things, for example, permutations. So one way is to prove that so what is a permutation is that you have A1 to AN and you have B1 to BN, as that they actually change the order of that somehow. But every element is there. And one way is that the verifier gives us a challenge and we prove that these two polynomials are the same, because they have, now these polynomials are 0 for x is equal to A1 or x is equal to A2 and so on, and you can prove that both of these exist on both sides. And then you have polynomials characterizing both of them. You can also do matrix operations with that, so you have a lot of power of arithmetic circuits. And can we do a bullet proof for some kind of arithmetic circuits? And this is called the arithmetic satisfiability problem. So that we are given an arithmetic circuit like that one here. And we also given an output, but we don't know the input. And the question is, does an input exist such that this is true? And in this example, there exists one, you can say 3, 5, 5, 3 is one which is satisfying this equation, because 3 plus 5 is 8, and this is minus 8, and 5 plus 3 is 8, and this is 0. and here 3 times 5 is 15, and here we get minus 15, and here, no, we get plus 15 here, sorry. And then here we get minus 15, and when we add it, and it's a 0 as well. And this is the arithmetic circuit which proves that x1 and x1, x2 are the same as x3, x4, but maybe switched. We already have seen that. So that's with arithmetic circuit doing that. So now in the zero knowledge setting, we know we have an instant which has this property, and we can build a very complex arithmetic circuit, and we want to prove that all the operations, all the secret informations are correct, and we get the publicly known result at the end. So that's the arithmetic satisfiability problem. And can we build a bullet zero knowledge proof for that with the things that we have already seen? Now, this is the short answer is yes. The long answer is let's see how we do that and describe it. So publicly known is we have a circuit. The circuit structure is known from the beginning, and the proof and verify knows about this. So basically, this is the task. And so we know that there is an input gate X, but we don't know the value. So the values itself are secret. The output is public. We know what's the output, and we have and we have all the constants are also given. Okay, so that's a problem. So can we build a bulletproof? It proves that for these unknown inputs, that the correlation holds. Now this can be done very technically, and we have actually two problems. So the first problem is, we have two kinds of gates, addition and multiplication. The constants are not so big problem at all. So what we do is we write down all these multiplication gates are numbered as A1, B1, C1, A2, B2, B3, and A2, B2, C2, sorry, and A4, and so on. You get the idea. So we have all these things, and write them down as you have vector A1 to AN, and then we have B1 to Bn is equal to C1 to Cn. And you can see that this is the Hadamard product. So we could write this out. So we could say, okay, we can make a Hadamard product if we have commitments for all of this. But what do we do with the rest of that? Now, for the rest of that, we just start to number all edges. So this is H1, this is H2, this is H3, and so on. We give each edge a number. And we describe everything which is happening in the circuit without the product. So we say, okay, E1 is equal to the first input. E2 is equal to the first input. E3 is equal to the second input, and so on. And so on, and so on, and so on. And this is done. And we also say that E17 is 0 and E18 is 0. So basically what we have is, we have a matrix operation of all the E's such that we get input and output. Just has zeros and ones in this matrix. A huge matrix where you multiply this, where you have all these E1 to EM, and the other side you have some X1, XN, and you have some Y1 to YC. And you have this matrix which says, okay, at some positions we have some ones here. So very small number of ones here in this matrix. The rest is 0. So that's the first matrix multiplication. Okay. Then we have to describe all edges and multiplications. So when we have to describe where these are fed into multiplication, so we have A1 is equal to A9 and B1 is equal to E10 and so on. So which is again a matrix multiplication with the edges here. So we have on the one side we have the edges, and the other side we have the vectors for inputs A, B, and C. Again, the same thing. So we get these very easy equations which are linear. Okay. So at the end, we have to describe all edges which come from from constant gates, or which go into addition. So this is the only thing that the matrix is doing anything. So for example, E10 is equal to E1 plus E2. So this is this one. So if E1, we have E2, and this is E10 here. And we have to write down all of this as well. And so we get a bunch of very easy equations which are given directly from the description of the circuit, because at some point it's written down. Okay, so what you have to do is, we as the prover compute all the values and we commit to all of these values. Now but the cool thing is, we can commit to E with one number, we can commit to A, B, and C with one number, because that's the idea of this Peterson commitment, that we can actually take a huge number of possibilities and just make one number out of this and commit to this. So all the numbers here can be committed to one value, but then we have to prove that this committed value, which is somehow encrypted with El-Jamal, with exponentiation or with elliptic curves, has the properties. And that's what we can do. So we do a zero knowledge proof for multiplication. We do a zero knowledge proof for the addition. So we do a zero knowledge proof for matrix multiplication and so on. And we know that each of these zero knowledge proofs has a logarithmic number of messages. Okay, now you could say, okay, but this matrix is huge. It's number of inputs times number of gates, or maybe it's the number of multiplication gates times the number of edges. But this is still the logarithm. So if you have a logarithm of m times n, then this is the logarithm of m plus the logarithm of n. So you get O of log n. Even if you have quadratic runtime, it's still order of log n. So that's a nice thing about logarithm. We don't have to care what kind of values you have. Even if the matrix is huge, we don't have to do that. So for communication complexity, it's very easy to do it. Yeah, so basically we are transforming this into two components. One is this component, and the other component is, so this will be a bunch of values here. It's not the A, B, and C from the multiplication gate. And the other thing is this Hadamard product of A1, B1 is equal to A1 times is equal to C1. So this is the thing that we have to do, and each of them has logarithmic size. And we don't have to construct the matrix in full, because we can actually, put in the values into the proof when we need it. We don't have to do it. We don't have to store it somewhere. Okay, prover and verifier can do this in parallel, and so we have a zero knowledge proof for arithmetic circuits, and arithmetic circuits can do anything, because they can do Boolean circuits. You can transform a Boolean circuit with constant overhead into this. So everything which has a Boolean circuit of polynomial size has a bullet proof of logarithmic size, because you can build an arithmetic circuit, and with arithmetic circuits you can do this Hadamard and matrix multiplication, and then it boils down to very short proofs. Which means now we can, the number of messages for everything which you can reasonably compute in logarithmic time, in polynomial time, is logarithmic. And that means you don't have to transmit a lot. And if you look at the complexity, it's also not that large. So what can we do now? Now, if you look, so arithmetic circuits, something we have seen. So in the paper of Bünz et al., there is a shorter proof for showing that you from an interval, that you choose a value from an interval. Shorter in the sense that it's a smaller constant factor in front of the logarithm. That's the only thing. Otherwise, if you just do it with a Boolean circuit, you get also log n. Permutation is something very interesting. Yeah, many more applications. And these bullet proofs can be always transformed into non-interactive proofs via Shamir heuristic. And even polynomial large folding products have logarithmic proof size. So everything goes down to logarithmic proof size. There are some tricks to improve the complexity of a verifier so that this is smaller. And every time we use this exponentiation, we can use elliptic curves as well. And elliptic curves have smaller key size, so you spare a constant factor. Yeah, and this is finished. This is the reason why I wanted to do this lecture in the first place, because I want to show the challenges of bullet proofs. And the last thing is to summarize what we have done here. Probably you have forgotten one or the other thing, where we start and where we ended, and to see where we go from here. So if you look at the material, so everything before the bullet proofs and the zero knowledge proofs is from the book of Delfs and Knebel. So I found a very helpful book, which is called, I think, Compressed Sigma Protocols. Unfortunately, I found it yesterday. I would have loved to find it half a year ago. It was published 23, and where you get a very nice presentation of Sigma protocols, and you can find this in Elias. I uploaded it there as an electronic book. Some zero knowledge proofs are simplified for the lecture, and so if you want to implement Do Not Trust them, just please go to the original papers or look in the books with materials that I have given to you. So that is otherwise might not work. I'm not, I would, at this moment, I would ask somebody, I would sit down and have to prove for each of them that all the properties are fulfilled. I want to remind you to written exams. So one is on end of July, 31st of July, in the cinema lecture hall, and there's one in September. You do not have to register with a university system for the first one on end of July, but we had this survey, if you want to participate, going on, and so you can take both of this. I will publish a first exam on Elias, and I will also publish some alternative exams for those taking this exam, where they can see what kind of question I will asking. So I made the survey, so in both a piece of paper is allowed. I have not specified the size of the paper because I want to see what's happening then. That's why it can be very small, it's or very large, social experiments. I want to see what's going on. If you want to continue in this area, so there will be projects and theses, and I'm planning to actually have scheduled a meeting for the 18th of July, which is this Thursday after the exercise. And you can, if there's a small number of students interested in project and thesis, and I want to show what I want to do with bulletproofs, because I want to apply bulletproofs to a research area which is very interesting for me, but it's not so interesting that I've presented it in the lecture. It's called Mental Card Games, and I have some ideas how to do it, and there are a lot of possible projects and theses which are in a theoretical way, mathematical way. There are some in the programming, and there's also some which also in the program we have different level in wisdom design and so on. So I want to show my vision of this on the 18th of July and what I want to do. And if you're interested in do project or thesis, or just interested to do what, just join us. Again, this is my office. If it's too many students, we have to go back to this room here, because this is this room here right now. So we go there, and then I see 20 students, I come back. But if it's less than 10, then you fit in my office. You can also ask me during my consultation hour, which you find on our webpage, if the webpage is working. This week it's on Wednesday at 11 a.m. Next week it must be different. So what we have done, we looked in Kerckhoffs's principle. Is it good? Is it bad? We don't know. Security is different from cryptography, and cryptanalysis is the second part of cryptography. So this was the beginning, the first lecture. We looked into block cipher, DES. I think we didn't do DES, but we did do AES, and we introduced finite fields. We had cryptographic hash function and the birthday attack. That was a classic. Then we did a lot of things. And so this fifth lecture doesn't mean the time, it's just the slides. So we have extended Euclidean algorithms, we have Galois fields, residual classes, modular exponentiation, Chinese remainder theorem, RSA, reverse Chamy-Edelman, and we had primality tests as well, something. We looked in prime numbers are important. And then we had RSA again, Rabin's code, El-Jamal and elliptic curves, which are then the thing that we used later on. We talked about digital signatures, which are strange for elliptic curves somehow. And also for El-Jamal, they're more straightforward when it comes to RSA. And then in the end, we started with zero knowledge proofs. And we had perfect zero knowledge, Fiat-Shamir heuristic, and the bulletproofs for vectors, products, all kind of products. And finally, that's what we had just today, are arithmetic circuits. I think the list is longer for the things that we did not do. So when I did the lecture last time, I was introducing quantum cryptography using Prasad's scheme, which I think took me 3 weeks, because first I have to introduce what's a quantum bit and how to do quantum operations, and then we have to show how to do a Prasad scheme which is a secure way to do secret communication without the problem of transmitting secret keys and using the entanglement of quantum bits. Very nice algorithm. And there's a lot of experiments right now, practical experiments, what's the kind of distance that you can make with a quantum cryptographic channel, which is very interesting from a physical point of view. I think from a theoretical point of view, the main problem is error correction, because quantum bits are always some kind of analogous thing which are influenced by the environment, and if you get too much influence, then you get into some problems and you lose your data at some point. We have looked into zero knowledge proofs, but we have not looked into IP is equal to P space and Arthur Merlin games and things like that. So the kind of zero knowledge proofs that we did was only a small portion of all interactive proofs. So there is a lot of things going on, and it has also a lot of influence into computation complexity, where they showed that, we started with game theory where we have quantified Boolean formulas and P space, but then the proofer verifier concept was very interesting if we allow the prover to know maybe NP hardness, or you can maybe what can you prove to verifier that this is true. And this is called interactive P, is IP, and you can show that if a verifier has polynomial time algorithm, then you can only prove, or you can prove any P space problem. Of course, for this, the prover must be some kind of superpower. So if you one day meet God and he tells you his secrets, the only thing you can understand is P space. Because maybe even if he has infinite power, that's the best we can, he can actually prove to us. No, I don't believe that this will happen, mainly because the first person is a fictional character. So another way to do cryptography, completely different way, is private computation. So you can hide things. Now, by computing, by having some secret communication, so I can, we could make a protocol and compute the average amount of money that we have in our pocket right now by me just giving you a random number and you adding your pocket amount to him and to this random number and give it to him. And then it goes around, and then I remove my random number and give you the sum of all of zurück, back, and then you have the sum of everything, and nobody has revealed anything. So this is called private computation, and has a lot of interesting protocols which do not assume, have no security assumption, except that everybody is playing by the rules and not publishing any secret information. And here, you could also do things like Sharma secrets sharing, where you actually maybe have 5 people, and if 4 of them meet, then they can decipher the secret, and any 4 of them can meet. So you don't need the 5th person in order to get the secret out of this. And following here, you get trusted coin tosses, and at the end, you end up with mental card games, where you play card games without trusted third party. So you shuffle cards, you give it to the next one, and everybody can prove that this is the card you're playing. And you're obeying the rules. So, okay, quantum proof cryptography. Quantum proof, there's a dash missing. And I think it's not, it's VE. Quantum proof, no, I'm not sure if it's a quantum. So what is quantum proof cryptography? It's not quantum cryptography. It's because there is Shor's algorithm. Shor's algorithm is an algorithm where you can solve RSA, you can solve El-Jamal, and you can solve elliptic curves. So that actually everything that we have done is useless in this lecture if we have a quantum computer. Which is bad for cryptography somehow, because the only thing which is safe is quantum cryptography and the num cipher. And for the num cipher, you have to carry the key in the same length from A to B. Or is something else. And, you know, many researchers believe that lattice codes are quantum proof. So that if a quantum computer comes, it looks at your lattice encryption, lattice code encryption, and says, what? Can still decode it somehow because it uses a complete different principle. Which is basically what you have some kind of grid. So this is a two-dimensional grid, so you have 2 vectors. Okay, don't move it. And you have one vector x, and you have another vector y. And then you have multiples of integer numbers of this x and y, which form this very nice grid. But you don't do this in 2-dimensional, because that would be easy. Do this in 100-dimensional vectors. And the problem is that you know, you get this grid. The problem is to know what is a short representation of this grid. Because by some way to add a long vector, some vector combination, you might get a shorter one. So what you do is you start with a short vector, diagram, where you have a grid in 100 dimensions, and then you add some random numbers, and you get long vectors, and this is hiding the original information. Now, in order to encrypt something, you place a point in a real value space just close to one of them, which is important. Because if you hit it directly, then there's an efficient algorithm to do it. But if you just have, you know, just next to one of the grid cells, then you can find the original message using the original vector, but with the long vectors you can't, which is the idea of this lattice codes. That's how, in a nutshell, lattice code work. And it turns out that this is an idea which is very old, but comes back over and over again. And it turns out that you have to be very careful when it comes to parameters, how many dimensions, what is the length of these vectors, and so on. And obviously, quantum computers, there's no efficient quantum computer algorithm for that. Okay, If you're interested and want to a survey about lattice codes, is in the seminar next week on Tuesday here in building 51, ground floor, room 6. Lots of interesting talk. You can also click on this web page here if you have PDF and see the schedule. You don't have to come, just go to one. I will be recording all of this, and if the presenter allows, you can see the recording later on. I think there's nothing better than a student give a seminar presentation. Yeah, because they are so good, the students nowadays, in presenting things, so you can give this away directly as a scientific talk, I guess. Or what do you think? Have you been to a seminar? Okay, so you don't get the joke. Okay, no, it's not a joke. If you're interested in project and thesis, again, Thursday at 2 p.m. In my office or here, depending on the number of students, and you can also contact me during my consultation hour. And if you click here, you get you can see in the calendar of my group where when it takes place. Okay, so that's it for the lecture for this semester. I hope that you can take away something from that and you get some questions answered and you got some interested. Usually people get drawn to the cryptography by the name, and at the end they get tossed away by the mathematics. But for me it's quite a difference. I really like the mathematics and that it can with application, and I hope that you enjoyed it also. So thanks for coming, and don't forget to exercise on Thursday.